Hey guys, this is the second video for the Boolean Algebra series. We will be discussing Boolean Algebra identities, how to prove them. I won't be proving all of them, but I'll show you how we actually go on to prove them and probably make the concept a little more clear for you. And we will then use those to simplify expressions, do past paper questions on that, and yeah, let's get started. So guys, this is our list of identities. There are quite a few of them, but most of them just come with logic. The first 6 or 7 of them, you will understand them pretty quickly. So our first one, and also something you should remember, is that for the AND gate, as we saw in the last video, we use the dot notation, and for the OR, we use the plus notation. What that basically means, let's look at the identity law first. So over here, 1 dot a 1 dot a is equal to a. That means if you're having an input of 1 and then a, right, a is just another input, but 1 necessarily means that it is true, right? An input of true, and a processed via an AND gate, the output of that would be a, right? Pretty simple. So a, if a is 0, and for example, if a is 0 and our other input, which is fixed, which is 1, is there, our output will be 0, right, which is the value of a over here. So the same thing that shows over here, we will get here, right? Okay, now let's move on to the OR form for this. The OR form is also pretty much similar, as you can see, right? We have 0 and a. We to prove this, we will do the same thing, right, for every one of them. That's why it makes this topic so much simpler and easier if you actually know what's going on. So 0 and a, if our input for a is 1, right, then our output will be 1. If it is 0, then our output will be 0. Now this is the identity law, but in this case, instead, if we had 1 plus a, right, 1 plus a would not give us a. That is not the identity law. This is important to remember, that for the AND gate, we have 1 dot a is equal to a, and for the OR gate, 0 plus a is equal to a. The logic is pretty simple, but it's worth remembering this point. Okay, then let's move on to the next one. It's the null law. Null law. So if we process an input of 0 and a, right? So if even one of our inputs in an AND gate is 0, the output will be 0. That's what the null AND gate, null law for the AND form means. The null identity for means for the AND gate form, right? And in an OR gate, if even one of our inputs is 1, the output will be 1 anyways. So that's the null law already done. A idempotent law. I'm so sorry, I cannot pronounce this correctly. It means that if both our inputs, right, if we have identical inputs, a and a, let's just draw this like this, right? If we have identical inputs a and a going through an AND gate, right? This is for the idempotent law, right? We have a. Now, if the value of a is 0, both of these will be 0, and our output will also be 0. If our value for a is 1 now, our output will also be 1. Now for the OR gate, it's the same thing. If you have similar inputs, the output will be the same. Now let's look at the inverse law. Now if you remember, in the last video we looked at notations, and when we have a dash over our input, it means the complement of that. So if my a is 0, it will become 1, right? So over here we have a dot a complement. So in that output, in our logic gate, we will have a, if we are setting the value for a to be 0 in this case, the a complement will be 1. Now you see, we're doing Boolean algebra, which is of course based on binary, so we will only have 2 inputs, either 0 or 1. So if our complement becomes 0, then our output will have to be 0 for the AND gate. Otherwise, if this is 1, this will become 0. So our output is going to end up being 0 anyways. Or if our A is 0, then this will be 1 and our output is going to be 0 anyways. That is the inverse law. Now let's look at the OR form for the inverse law. A plus A complement is 1. The easiest way to learn this, using of course logic gates, right? Let's draw an OR gate. Over time you'll probably just get this. You of course don't have to draw these logic gates every time you solve some questions. It's basically meant to make your life easier. When we have complex logic circuits, you can use these and simplify your expressions. That's why we do this. Okay, so inverse for the AND gate. If we have A as 0, our A complement will be 1, right? Now since it's an OR gate, the output has to be 1. And if this is 1, of course this will become 0 and our output will be 1 either ways. Okay, so that's it for the inverse law. Let's look at the commutative law. The commutative law is A dot B is equal to B dot A, which means it doesn't matter if you switch the inputs. It doesn't matter if this is A and this is B, or this is B and this is A, right? Our output is going to be the same anyways, which is pretty really logical if you look at it, and I won't really be proving this because there's really no need to. Let's look at the next one. The OR form for this, A plus B is equal to B plus A. Same logic. Let me just draw the logic circuit, so probably it'll be a little more clear. AB is equal to BA, right? I'm sorry for my drawing again. I really try to make it better, but this is what happens when you try to complete it a little faster. Now let's look at the associative law. A dot B dot C is equal to A dot B. We're looking at the AND form for the associative law. A dot B is equal to dot B dot C. Okay, so now let's draw the logic circuit for it. Maybe it looks a little complicated, but it's not. Just simply add an AND gate where you have the dot, and if you have a plus sign, you add the OR gate. It's pretty simple. We have an AND gate first, A and B over here, and then we have the input C. All of this again, it's going to be processed through the another AND gate, right? C, and we have our X. So it means that this input is this logic circuit's output is equal to the logic circuit output for this, where we have B and C, the output for this, and we have A passing again through an AND gate, right? The output for this will be the same. If you're really diligent about this, you could probably pause the video over here, probably make some truth tables when we have A, B, and C, and actually solve it out. What you'll see is that for every combination of A, B, and C, for both of these circuits, the output of X is the same. That is why we have this law which says this is equal to this. Something important when you draw logic circuits is that whatever comes in the brackets, that is what you have to draw first. It's kind of like simple algebra. What happens in the brackets, you kind of do that first. Okay, so now for the OR version of the associative law, I'm not gonna really change a lot, right? Yeah, of course, the law is different. Here we have A plus B, the bracket plus C is equal to A plus bracket B plus C. Over here, all you really have to do is change these AND gates with OR gates, and then you have the same the circuit you need basically. That's all I'm gonna do. I'll erase the AND gates and I'll draw OR gates instead of them. make sure to draw this much better when you're doing it in the exams, um, because yeah, these carry marks. They have to be pretty well recognizable. Same thing over here. If you go on to make the truth table for both of these, for combinations of A, B, C for both of them, the outputs will be the same, right? Um, so now let me show you how to do the distributive law, right? For the distributive law, I'm going to solve the whole thing. Okay, I didn't really want to erase that part. Yeah, let's do the distributive law now. The distributive law. Let's solve the and, right? Yeah, let's on the and form for this. Our distributive law is A plus B dot C is equal to A plus B dot A plus C. Yep, A plus C. Okay, so let's make the logic circuit. I'll choose another color. We have an A input A, right? Then we have inputs B and C. Inputs B and C. Now B and C are passing through an AND gate. Let's make an AND gate, right? And since we have a plus sign, we know that the output for B and C passing through an AND gate is now passing with an OR gate, right? Taking input from A as well. Now this is this side of the law. Let's draw the other side of this. This is equal to, here we have A plus B, right? So an input A. Okay, if we can see that A is common in both of these brackets, so let me just draw A in the between. We have A. I'm going to split these, take B over here. Since it's a plus, let's add an OR gate, and we have the output, right? C. Again, we have an OR gate. Should have probably, just give me a second, I'll draw this a little closer. C over here, yeah. Pass this through an OR gate as well. Make the drawing look a little better. Okay. So we have the first part, but now both of these are passing through the AND gate, which is the dot over here, right? We have both of these inputs forming the inputs for the AND gate over here. Okay, and this is our final output X, right? Okay, so you can see how one complicated circuit is equaling to another complicated circuit, but the truth table for it, as we're going to see, is going to be the same, right? And how you can use these is something we would do in expressions when we solve expressions, and it makes it a lot easier if you remember these laws. Okay, so now let's make the truth table for them. I'm going to make half kind of truth tables. I'm not going to complete it, but my purpose for showing doing this is showing you that in fact, yeah, the truth tables do give us the same outputs. So let's start with a 0, 0, and a 0, right? If B and C is 0, the output for this over here will be 0, and if all of even our A is 0, the output will be 0. Let's come over here. If A is 0, right? If A is 0, B is also 0, and C is also 0, we'll have zeros up till here, and then the output will also be 0. Now let's take another combination. We have 0, 0, and 1. Okay, now let's look at B and C first. 0 and 1 passing through an AND gate gives us a 0 anyways, and an A is already 0, so our output will be 0. Right over here, we have 0, 0, and 1, right? So if our A is 0, A and B over here, this part is going to give us an output of 0. But since our C is 1, this will give us a 1. But we're passing it through an AND gate anyways, so if we have 0 and 1, the output is going to end up going to be 0 anyways. So you can see it's exactly the same. The outputs are the same for the same combinations. Okay, so let's just fill up the rest of the table. So with 0 1 0, we'll have a 0 again. Please go through your working and make sure that even you're getting the same answer. Next we will take 0 1 and 1. Okay, notice something over here. For this one, if A is 0, right, and B and C are 1 and 1, right, one of our inputs till here will be 1 and the other one will be 0, which means our output will be 1 actually here for the first time. The same thing will happen over here, 0 1 and 1, right? So if let me just erase some bit of this so it gets easier. Right, okay. Yeah, so we have 0 1 and 1. So if our A is 0, right, A is 0, and B and C are 1 and 1, which means the output till here for both of them, since these two are OR gates, both of these are OR gates, our output till here will be 1 and 1. And when 1 and 1 pass through an AND gate, of course our output will be 1, right? Yeah. Okay, let's look at just one more truth table values. 0 1 0 0 and 1 0 0. Over here our B and C is 0, right? So this is going to end up being 0 over here. Since both of these are 0, this will also be 0, but our A value for A is 1, right? So our output for X will also obviously be 1 since it's passing through an OR gate. And without calculation, and I can be perfectly sure, the same thing will happen over here and our output value for X will be 1. Alright, so we have proven the AND form for the distributive law. In the same way, you can also do the OR form, right? The OR form, which is right over here. You could do this too using logic gates, but I'll just write it down because I'm writing all the laws down, right? The OR form for the distributive law is A dot B plus C is equal to A dot B plus A plus C. A dot C. So if you've probably done maths, you'll probably realize this, right? When we have x and then y plus z, right? What you get is xy plus xz. Yeah, it's the exact same logic here. All right. So next we have the absorption law. Let's look at what the absorption law is. In the absorption law, we have A dot, this is for the AND, A dot A plus B is equal to A. If you make the truth table for this, you'll understand why this happens. I wouldn't be doing it right now, but this is obviously and of course very important. If you don't want to prove it, you could just remember these two laws, these two forms for the absorption law, this one and this one over here. Then we have the De Morgan's law, right? Let's do a little bit of proving for this. Maybe not draw full truth tables, but just a little probably tip about how we will go about remembering it, right? We have De Morgan's law. The AND form. A dot B, the whole complement is equal to A complement plus B complement. Okay. There's probably some explanation with sets over here which you could relate, but it's best and it's easiest if you just remember it, right? The reason is these are really easy to remember. When we have a plus in the expanded form, we get a dot, and when we have a dot over here, the expanded form, we get a plus. Yeah, it's basically just that much. the double complement. Okay, the double complement is basically our logic. Okay, the double complement. Say we have a term, right, in a single complement, right? When we do this, it means our 0 will turn to 1. If our initial value is 0, it will turn to 1, right? But what if over here we call this y and we complement it again, right? It basically is we're complementing a 2 times, right? Then our 1 will turn back to 0, right? Be z. Let's just call it z for right now, but it will turn back to 0, which means if you're complementing the same value twice, right? So 0 turns back to 1, and then it turns to 0 though. If we have 1, it will turn to 0, but then it will turn back to 1. Since it's binary, it has nowhere else to go. Therefore, the double complement law is it's just common sense. The double complement of any value is the value itself. That's all it is. Okay, guys, so if you've made it till here, give yourself a pat on the back because it only gets easier. Probably more fun from here, right? Okay, let's solve a few examples now. So I'm taking this question first. It's a random question, a dot a plus b. Okay, this is a dot. Now let's solve this. So first, how would we go about? Remember simple mathematics, we have this, we just expanded xy plus xz, right? So we will have a dot a plus a dot b. Now if you remember, a dot a, which is true and true, will give you 1, right? Then we'll have 1 dot b. It'll give you a and a, right? Pass it through a logic gate, it's gonna give you the output as a. Okay, now after this, let's remove a common. We'll have 1 plus b. Okay, and if you remember, 1 plus b, just gonna draw the logic gates just to explain it to you for some time. We have an output, right? 1 and this, so it doesn't matter whatever b is. If it's 0, we'll still have our output as 1. So this would be a dot 1, which is obviously a itself. So you can probably see that we have solved such a decently complicated logic expression and just gotten a very simple answer, which is a. Okay, so this is basically the use of logic identities. Let's move on to another example. The second one, I'll try to make this a little more complicated. A b complement c complement plus we have a complement b c complement plus a complement b c complement plus a complement b c plus a complement b c complement. Believe me, this is really easy. Okay, over here, let's just look at what we can take out as common first. So we have a complement over here and here as well. We have c complement here and here as well. Let's take that out as common. So we have a complement, c complement. The bracket, we'll have b complement plus b. Okay, now a plus sign. Let's see what we have common in the second next two terms. We have a complement here and here. And no, c is not a common, right? Yeah. B is common. So that would give us, we'll take a complement outside and b complement outside, right? So we'll have c complement plus c. And then the next one, am I missing a term? Probably missing a term. Let's just go with the same thing right now, it doesn't matter. We'll have a complement b and c complement. 2, 3, 4, 5. I actually had 6 terms in the question. Let me just check. Oh yeah, we had another one. Let's just solve that later as an additional example maybe. So what will we do over here? Since we have b complement b, You probably remember this is the inverse OR law, right? Where we had a plus a complement giving us 1, okay? So it doesn't matter if it's a, b, c, whatever input it is, if the input plus its complement, the answer would be 1, right? True value. So that would give us a complement, c complement, and then 1, plus over here a complement b, and again 1, plus a complement b, c complement, right? So we'd have this, this, and this. Can we further simplify this? Let's look at it, okay? Yeah, we could probably take out a complement common for all of these. We'll have a complement, c complement plus b. Right, we took out a complement. We have c from this term, b from this term, and b and c complement over here. Let's see what happens. A complement. Probably take these two terms over here, b plus c complement and b c complement. Okay. All right, a complement. Now we could remove c common again, right? So c complement. Would it be better to do it the other way around? Let's see. So what we're gonna do right now is take b complement, b common, right, out of these two terms. So we'll have 1 plus c complement, right? And of course, the other c complement, we cannot forget this, right? So, okay, now 1 plus any input, right? 1, let's look at this. We have an OR gate right over here. Let me just draw it a little better. We have an OR gate. We have our input as 1, and which is 1 over here, and a c and c complement, right? Our output, since it's an OR gate, it'll have to be 1 anyways. So this whole term, it becomes 1. So we have b 1 plus c complement in the bracket and an a complement outside. Now what we get was a complement, b plus c complement, and to simplify this term, we'll have a complement b plus a complement c complement. Alright, so if you have any doubts in this question, please post it down in the comments and I'll try to solve them as best as I can. Now let's take another question. This is pretty interesting because it's another way of proving the distributive law. So our distributive law was a plus b dot c is equal to a plus b and a plus c. Alright, so now let's expand these brackets. I'm not gonna skip any steps, but in the exam you could probably skip some simple steps like these, right? That won't be an issue, I guess. We have a plus b over here and a plus c over here. So a dot a plus a dot b plus c dot a plus c dot b. Let me just rewrite this a little bit over here, make it a bit simpler, right? Now what you should recognize and what you probably will get with practice is that a dot a, right? Just think of it like this. What happens when you see something weird or something familiar? A dot a, our dot sign means it's an AND gate, right? So if you don't remember it on the spot, you could draw an AND gate. We have two inputs, a and a. What would it give us? Our output would be a itself. So a dot a becomes a. Then we have a dot b plus c dot a plus c dot b. So alright, after this what happens is really interesting because yeah, let's just look at it, you'll understand. When we take out a, we'll have 1 plus b plus c and then c dot b, right? So what happens over here, if you remember, is when we have 1 plus a, right, we're passing it through an OR gate, right? So our output will be 1 anyways, right? So when we have 1 plus b, our output should be 1, right? So that term is kind of negated. Then we have 1 plus c, cb. We move ahead, we remove c the same way. we have this plus CB, and yeah, we're moving closer to our answer. 1 dot A, as we know, is A, CB. So if you can actually notice, I've proven the distributive law here via logic expressions. All right, let's move to past papers. Right. So I have a solved one over here, but let's do it again. Okay. Just gonna blur this. Let's erase it later and see if our answers are right. Okay. Write the Boolean expression corresponding to the following circuit. Okay, so we have our inputs A and B. Let me use a different color. We are inputs A and B, right? They're passing through an AND gate. So we will use A dot B passing through an AND gate. Just put the brackets in. Then I have a C, right? So C, so A dot B plus C, because the input from A dot B is passing through this OR gate for C2. Okay, so we have completed our circuit till this part. Next we have an AND gate coming up. So our input from this, which is the output of what we output till here, right? And we have the AND gate. So the whole thing in the brackets and an A, right? Let's check our answer if we're correct. So A dot B plus C. Yeah, you should probably not forget adding the dot, at least for A levels. Otherwise, it's not really required. Okay. In the next part, we are going to be simplifying this. Okay. Use Boolean algebra to simplify the expression that you gave in part B1. Right, so let's expand it. We have A dot B plus A dot C. We remember A dot A is going to give us the output as A. Right, so we have A dot A plus A dot C. Can we simplify it further? Probably take A outside. Wouldn't matter a lot, I guess. We have B plus C. Let's check our answer. Yeah, that's the same thing. Add the dot over here. Yep. Okay, now let's move on to the other one. Alright, so I've already blurred the answer over here. I would recommend that you pause the video, try it for yourself, and then look at the solution. Right, so we have A and B passing through an OR gate, so that will be A plus B. Adding a bracket, then we have C, so the input, the output from A dot A plus B is going into the AND gate with another input of C, right? So we'll add a dot sign C. Okay, so now this is forming the input for the next AND gate and A. Alright, this is forming the input and A over here. Right, now let's check the answer. Yep, that's the right answer. Just reshuffle it a bit if you like, but it's gonna remain the same thing. A plus B dot C. Yeah. Of course, you can write C here also. All of these are the same. If we put C over here and then we have A plus B, all these three, they are all the same and all are correct. Okay, so now simplify this expression. Alright, let's do that. I'm gonna erase the other ones for now. It's already using any of them. We have A dot, oh, I'm not gonna open the big brackets as of yet. So put it C dot A plus C dot B. Okay, and then open the brackets a little more. We have C dot A plus, I'm gonna write it as ABC, probably a little easier to read. ABC, right? I have the dots in between, and then we know A dot A is gonna be A, so we got A dot C, just writing it alphabetically. ABC. Could probably remove AC common. I'll have 1 plus B. Now, if you remember when we are proving the distributive law, right, we have 1 plus b. What does it form? 1 plus b is, again, 1. So, yeah, our answer should be AC. Let's see. Yeah, that's our answer. Alright, guys, so next time we'll be covering K maps and full adder circuits, half adder circuits, and flip flops. Alright.